So, in this lecture, we will again continue our discussion on shunt clamping circuits, but in terms of component determination of the circuit, we will be following a discussion where we will like to find the components of that clamping circuit where resistors, capacitors and diode which are involved in it. So, before entering into the discussion, let us remember previous discussion where we were talking about time constant of an electrical circuit. Tau. For this time constant, we have already discussed in terms of discharging of the capacitor, and in which one resistor were involved, where R1 was the resistor and C1 was the capacity of the capacitor. So, time constant became R1 C1. Now, there one diode was involved, and together we were discussing where diode was like a ideal part of that circuitry. It was there when discharging was happening and time constant was found. Today, we will discuss in another way. It is not for discharging, it will be for charging of the capacitor. So, for that, let me first discuss about a small circuitry there to understand about fundamental things which happens in charging of a capacitor. Like, say one capacitor is connected to an electrical circuit, say this one, R and C. In that, you have applied one signal which is of the kind we were seeing in our earlier class, where the voltage is going from plus E to minus E. Let us begin with this circuitry where this electrical voltage, if it is applied to this circuitry, what happens to the capacitor charging? At the beginning, when you apply this voltage, it will go suddenly to plus E. Do you expect the voltage across the capacitor will become E? Now, after your idea on this time constant, which is now in this circuitry, it is becoming R into C, the way it was found in the last class, that if in a circuit resistive path, total path follows the resistance of R and capacity of C, the time constant will be RC. What does it mean? It needs, it requires a time to respond to the system in a particular fashion, where to complete the charging of the capacitor to the required voltage, it will take time for doing so. It needs a time constant for which it will be reaching at least 90% or above, or a particular percentage of the peak voltage at this time. Let me discuss little bit elaborately on this part at the beginning. Say you have applied a potential of 5 volt. In that, this voltage, is it directly coming to this at the instant when this 5 volt is just switched on? What is the voltage at that instant when the switch is on? Can you tell me the voltage? The voltage should be 0, because the capacitor cannot charge instantaneously. Does current flow through it? In that case, you will say yes, current flows. Why? If you say 5 volt you have applied here, and through this circuit, through this path, you are seeing some potential drop supposed to come here and supposed to come here, which has come 0 now. If the potential is 0, it is effectively a short circuit. So, in that case, the current which you will see here, that is nothing but 5 by R. Okay? But you are saying that potential through this is 0, but still current is flowing. Maybe some confusion arises there. For that, you have to go for this equation. Which is a continuity equation for a capacitor, where if the rate of change of potential is there, current through the capacitor is possible. What is the rate of change of current here at the very beginning when it is going from 0 to 5 volt? Rate of change I am talking about, not the potential, because current through the capacitor, that decided by the rate of change of potential difference with respect to time, not on the absolute value of the potential across it. But for the resistor, the absolute value of the potential which is coming across it, that will decide how much current is flowing through the resistor there. So, it is slightly different for this capacitive element there if it is connected. Fine. Now, if it happens so, some current is there non-zero, which is flowing as a highest value, I will say, because the potential here is 0. So, the current flowing through the circuitry is fully decided by the capacitor itself, as if resistor itself, capacitor is not at all there. But immediately after current flows through the capacitor, capacitor will start charging. So, current is the cause for developing potential across the capacitor. Whenever some current flows there, some potential will get developed here, say that is 1 volt after some time. Now, if I ask you how much is the IR value then now? After capacitor voltage has become 1 volt, the voltage will become across the resistor 5 minus 1 and the current will become 5 minus 1 by R. So, that will be the current which will be flowing through the capacitor. So, now current is going down. And what is happening to the potential across this? It is going up. What is the limit up to which this potential will go across the capacitor? That is the question. So, one time will come there when this capacitor will fully charged with 5 volt. The time it becomes charged at 5 volt, the potential drop across the resistor is becoming 0. So, IR current is 0. So, when the potential across the capacitor becomes 5 volt or capacitor is fully charged with the applied potential, the current in the circuitry becoming 0, because the potential difference between these two parts is 0, but still potential existing across the capacitor. Now, here if I say from 0 to 5, to develop the current, it needs some time to go. What happens to this scenario? In this, I am saying input voltage is applied at this instant when instantaneously it is going from 0 to plus E. So, the capacitor will try to charge with that, but it will not able to. So, it will take some time to go up to that maximum value. How that time will be decided, that after a particular time this will go charge for a full E volt, that will be decided by this R and C values, where R will be in ohm and this will be in farad, and finally this will be of unit time. So, for this time it needs to get ready with the response which is applied through it. Now, this time constant I will be calling as time constant for charging. The way we were saying in the last class, time constant for discharging. Okay? So, this is the concept which we will be applying to our circuitry, which we have discussed in the next earlier class. Let us get it in this fashion, where one resistor and capacitor is also involved in the circuitry, which was not there in our earlier circuitry, where we directly charge the capacitor, maybe through a diode it was connected. No resistor was there during the charging. So, that problem we will take in today's class at first, and then we will move for another circuitry for shunt clippers. Sorry. Now, in this part, with our already analyzed clamper circuit, obviously it is a positive clamper circuit, what we have already discussed in the last class. Now, I have put this in a box so that I consider this total thing is a system. Is an electronic system where one capacitor C1, one resistor R1 and one diode D1 is connected in a particular fashion which has input terminals here and output terminals here. Say input voltage to this is Vi and output is V0. This is an individual system what we have discussed already. What happened to this quickly? If I recollect, we applied a voltage here that initially for the positive voltage it was making this diode forward bias. So, the voltage across this become Vf and it was immediately happening because this C1 through diode it faced nothing, any resistive path through it. So, it was charging quickly to this. But when it went for the negative, in that case this diode was open. So, this circuit was there for R1 and C1 which was discharging after some time with which went to a delta Vc potential difference with the time constant R1 into C1. That was the discharging time constant. Those are still there in this discussion today. Now, this is the system which is connected to a source which has also two terminals here output. These are two out terminals which may be connected to the circuitry there. Now, source of what? Source of energy say. This will be used here to launch to the system so that it will start working. While doing so, any practical system, if it is a voltage source, it will give the voltage along with which one resistive component will be coming to its path. What is it? Now, if equivalently I represent that source as Vs, it will have one internal resistance Rs in it and together it is a source which we practically use. Ideally, this Rs will be equals to 0, but practically Rs is not 0, but of lower value. That is another issue. Now, whenever you excite one system by a source, basically you are incorporating this kind of one circuitry to that. So, if I connect these 2 points, and throughout I like to analyze this circuit, which way the voltage across the diode will be there. Let us analyze. Things are exactly same, only this much additional thing is incorporated there. Fine. Now, in this, since I am talking about component determination, means if a source is given to you with a potential Vs with Rs of some value, say here 500 ohm, it is ohm. It is given here in a clamper circuit, one C and one resistor will be should be used there in such a way the purpose is served for charging or discharging in a certain time period, not beyond that. That means if it is discharging, how much it will discharge or how much deviation of it is allowed to you, that will be said beforehand. If it is said, then taking those to your analysis, you have to tell what R1 and C1 value you are allowed to use in this circuit, or to devise or to design and clamper circuit with a particular specification, how to proceed. That is our final aim. Okay? So, at the beginning, we will start discussing if one input voltage of this, which is going from plus E to minus E, where the width is T here, here also it is a T. The way we are considering the width of the pulse is T. Now, if this is the circuit where input has come in this fashion, what should be the output? We will start analyzing. First, we will see whether this diode is forward biased or not. Whatever be the resistors or capacitors connected to it. Because first I have to check if diode is getting some potential, how much is the maximum possible potential across the diode. Say full potential here has gone to this, which is quite above the threshold cut-in voltage Vf there. So, the potential here Vf, after it reaches, then the potential difference between this and this, or this and this, that will decide how much current will flow. Or another way I will say, if some potential is applied there, if some potential Vf has found here, then immediately I can tell the output voltage will be Vf first. The way we were having in our earlier analysis, say Vf for this part, the potential become Vf. But we initiated one discussion here in today's class that this capacitor charging will be getting disturbed by one resistor Rs, which has come in series with that C. What is about that? To know that, what you will do, first you have to analyze that what is the Vc potential. What is it? Vc will be if this person would not be there, that is short. If this would not be there, then what would be the potential across the Vc? Capital E. If R would be 0 and C1 would be of some finite value, Rs into C1 is 0, so immediately it would be charged, so it would be E. But since one Vf potential has to go beforehand, so that this circuit works, where R1 will be becoming just useless for this particular circuit for positive half. Okay, so some potential will be coming here, so it will be E minus Vf, the way we are considering the earlier circuit. Okay, is there anything remaining? Because the potential across the capacitor, now it is not like earlier we were considering E minus Vf, where potential was applied there and some potential went here, so the total potential minus this potential was coming across the capacitor. But scenario is changed here. Here I am saying maximum possible potential here is the potential this minus this part. So here it is IC Rs. This is the difference. Okay, due to which? Due to the source resistance Rs there. Does it really affect your circuitry? You will see after some time. See here, when it is in conduction at the very beginning, capacitor was basically charging from lower value to higher value, and finally it will be reaching to the highest one. The time it reaches the highest value, which can be gained by that capacitor, what is the current through it? Reference to our previous discussion. Current should be 0. If the current through it is 0, what is the potential drop across the resistor Rs? Obviously 0. So finally again it is becoming E minus Vf. But in between, before it settled down to its potential E minus Vf, and you are trying to measure the voltage across the capacitor, it will not give you E minus Vf potential, but less than that. Okay. So this is the effect of this Rs, and this Rs and C1, combination of that decides at what time you will get your actual voltage E minus Vf across the capacitor. That way the charging capacitor will be coming into picture. So if your potential is applied for this particular time, what is your guess? That how much should be the C1 value, so that you guarantee that your potential will reach up to this point? At least not less than, not more than this T. Because after this time, again capacitor will try to discharge. So before it starts discharging, it should guarantee its full potential across it, otherwise whatever you are analyzing, those are useless. Okay. So for that, this Rs and C1 should be such that Rs and C1 should be such that it becomes at least the width of the pulse. So that during this time that charging will be finished at least at this end, at this time, then let it go to the negative side and again let it do its own work. Okay. But since our circuitry here arranged in another manner, where the output of this system is diode, not the capacitor, the internal things is not coming into picture unless and until we look into the thing in between this. Okay. So even though this rising is happening there, but due to this diode, which is actually deciding the output voltage of Vf there, we are always with the Vf potential. But in between, diode is getting charged, which will be discharging in the next cycle, next half. Because when the potential goes from higher to this lower value, then capacitor will like to discharge there. We will see immediately after some time. Okay. So if this is the specification, we consider that yes, I will design one circuitry there so that the Rs into C1, that is at least equal to pulse width. So if pulse width is provided to you or frequency of the signal is given to you, in that case you will able to decide C1 if Rs is given to you, because if source is given to you, Rs is given, say it is 500 ohm. Now say this signal has a frequency of 1 kilohertz. If the frequency is 1 kilohertz, what is the T? 1 by F, half of it. If frequency is 1 kilohertz or frequency is F, what is the period of the signal? 1 by F. So this is the total period, and I am saying that is the half of that. So half of 1 by F. So it is basically 1 10 to the power 3 half, so 0.5 millisecond. Any problem? If I say this t is 0.5 millisecond, then RS C1, that is pulse width, that is equals to 0.5 millisecond. So please calculate the value C1 if it is 0.5 millisecond divided by RS is 500 ohm. How much it is coming? 1 microfarad. Okay. So for a given source with RS value this much, the C1 value should be decided at least 1 microfarad, so that the charging will be happening within this period. What happens to C1 value if RS changes? Obviously, if R is more, C1 will be required lesser. Okay. So this way you will be determining the C1 value to satisfy the charging. Now till now I have not discussed about the discharging, and in it how C1 is involved. Let's proceed for that. So, if you remember your previous discussion there, when this input went from positive to negative or minus plus minus to minus plus in this potential, that time the capacitor which was charged earlier plus minus, which could not respond to this immediate change at the capacitive voltage. So it will be retaining E minus Vf value. But what happens to it? If it would be minus E like earlier, because here it will be minus, it will be plus now. But if it is minus plus E, means minus E here, and here it is Vc, which is again negative sign of that. So total potential across these two terminal, which is actually the terminal of diode, which is now open. So that potential was minus E minus Vc. Any problem? V naught was minus E minus Vc. Now tell me, what is the potential now in this arrangement? With this consideration. Now your input is not here as minus E, but here. Earlier it was plus minus E, now it is minus plus again E. Okay. So in that case, the analysis goes this way. If some potential is applied there, let's see if that would go to the diode, what happened to it? It will be a negative potential here, negative here, positive here, so it is open. So diode, as if diode is not at all there in the circuit. But still I am saying some closed path is there in it existing. If it is happening there, still some potential is there at the opening at the output terminals which are available to me. That potential I am talking here. How much is that potential now? This potential minus this potential minus this potential. Okay. So if the current flows here in this circuitry, what is the current now? Current is flowing in other direction. So the potential after this, which I was getting in this fashion in earlier class, that we saw there, that this went up to minus E minus Vf. And what was the peak to peak voltage here? That was again 2E, because Vf has gone here, Vf minus of minus E minus Vf. So finally it became 2E as the potential difference. But the potential which came here, now that which was here at the beginning, that is now reverted to this way, where at the very beginning when the potential got inverted there, that potential here will become this potential into plus this potential plus this potential. Now if at the very beginning you say that current is now changing its direction, at that time the earlier current and this current has become opposite to one another, they have gone 0. But still the potentials are there. This potential and this potential with negative polarity. Okay. So now, but the capacitor was charged with plus minus here, which is not supporting the convention of the current which is flowing now. Actually, when through the capacitor current is flowing there, it should confirm that the current should flow from higher potential to the lower potential. So it is opposite to it. So capacitor has to discharge, because capacitor has the behavior that it will like to track this potential to which it will be trying to getting charged, so that the potential here becomes plus, here become minus. It's try actually. Circuit will allow or not, that is another issue. Okay. So in that we found that we went to a potential here, but slowly because of this current flow inside it, some discharging was happening, and there we defined one delta Vc, depending on the time constant R1, C1, which will be now different in this circuit. Now, if I ask you delta Vc to measure in this circuit, where the time constant has got changed, please tell me the expression first. What is the expression there? I think 2E into T by R1 C1. This was the expression. But for today, we will go in different route there, starting with another equation developing from IC into T divided by equation C1. This was the basic equation, del V by del T equals to 1 by C IC. This is the actual equation, where I have an objection now in this IC actually. That's why I want different expression for that. Okay. Now, if I want to develop this delta Vc expression for today's circuit here, then what is IC? First I have to find, because C1 is exactly same. I have not changed C1, and T is the pulse width what we considered earlier, still it is there. Only the problem change is that in the IC. Now again use the same idea what we took in the last class. How we found the IC? Means current through the capacitor is nothing but the current through R1, which was VR or V0 by R1. Is not it? Potential across this by R1, that is the current which was flowing here, and it was circulating through this capacitor and the resistor there. Now then, what was the V0 peak to peak we considered there? 2E. So finally it became 2E into T by R1 into C1. Okay. Now tell me what should be the 2E, what should be the peak value, VO peak to peak today? Earlier the peak to peak voltage was 2E. Now is that peak to peak voltage is 2E? Actually this voltage is the voltage which has come here, that is after minus IC into RS, that potential which came here as VI, that has gone to that place. Is not it? This is the effect of this RS which I am targeting today in today's class. So if I want to make it similar to the earlier discussion, then I have to consider not Vs as plus E or minus E, but minus of this potential which has come in this point as Vi, like in the earlier class we got. So basically the potential here has become Ic into Rs. This is the potential now. So if this is the Ic into Rs, this is the potential across this R1. What is the current through it then? The potential across R1 divided by R1 again. Now tell me what is the actual expression of Ic here. After taking this equation, Ic equals to this. I think you will find 2E by R1 plus Rs. Small manipulation. Simple mathematics. Okay. Now I would like to take this expression of Ic in this equation. So how it happens to it? Then the equation come 2E into T by R1 plus Rs into C1. This is the new equation what we have found today. What was the previous discussion? In that Rs was basically 0. So it became 0. So you got R1 into C1. Now you have incorporated another resistor, so it is Rs has come into it. But what is about the time constant now for discharging? I repeatedly said that in the path, the total resistive path which it will follow for conducting the current and the capacity of the capacitor which is in the path, those values will be multiplied. Now if I say this kind of one circuitry is there where two resistors are there, R1 and Rs in series, what is the equivalent resistance? R1 plus Rs. So that will be still there, R1 plus Rs, and that will be multiplied with C1. So this is the time constant now. Then if it is a time constant, what is so different from the earlier expression? Here the time constant has become more than earlier. If it is more than earlier, then to reach from here to here for delta Vc deviation, it will take more time. That means it will be running little slow. Means discharging will be little lower. Okay. So effectively the time constant should be considered R1 plus Rs into C1 there. Now if somebody asks you in this arrangement, if they allow you to deviate for this delta Vc or discharging through discharging for this pulse width is allowed as delta Vc is allowed 0.5%. Not beyond that. Means what? With respect to the maximum value, how much delta Vc can be allowed to this circuit so that it discharges before the next pulse come to it or next operation happens for charging this capacitor. How to find that 0.5? I think that 0.5 is nothing but delta Vc by total variation 2 E into, that is 0.5, is not it? So, this 0.5% tilting, if it is allowed for your circuitry, which is unavoidable actually in the circuit, but with that they ask you find the R1 value. I think you will proceed from this equation. Can I take this equation? Delta Vc by 2E into 100, that is actually 0.5. So, I will put this value here as 0.5. What is T? 1 kilohertz, half of that 0.5 millisecond pulse width. What is RS value? What is C1? You have already calculated 1 microfarad. Who is unknown here? Only R1. Please solve it. You will get the expression for R1, I think. R1 equals to 9.9 kilo. Please check it. So, if we go for component determination of this circuitry, we have to follow the path in this way, where we are able to decide R1, C1 and R1, C1 values such that the work of ours happens in such a way our tilting doesn't go beyond 5%. Doesn't go beyond 5% for what frequency? Again this 1 kilohertz. So, the signal which you apply here, how much is its frequency? That is very important for this kind of circuit arrangement, where capacitor will be charging or discharging. That depends on the pulse width, which indirectly depend on the frequency of the input signal. Okay. Let us take another topic on again clamper, but for bias clamping. Anything? 500. It is coming 500. This it is coming 500 ohm. Why this much less value? This is 500 ohm. This value is coming 500 ohm. Is it for all? I don't think. It should come very high value actually. But if you are saying, let's keep it. Let's check it further. No, this percentage is given to you actually. Delta Vc by 2E is given. Okay, please check this problem. We will go for the another discussion now. we have already analyzed some circuit for clipper in biasing condition if external bias is applied as VB1 there. So, for that, which way to change the connection here? By putting here plus and minus, then finally going to the ground. Those things I am not making here as a redraw of the circuit. Straightforward, I am considering if VB1 biasing is applied there in this circuit, that means it has a potential of VB1 with respect to ground, which is a positive. In this example, what I have considered, say 2 volt, plus 2 volt. Okay. Now, in this circuit, if I now analyze like earlier, I have to go for each and every potential for this kind of input where it is not a square pulse like earlier. This is the difference is incorporated here in this. Till now, we were discussing like one signal has put such a way that immediately at some instant it is going directly to plus E, it is staying there for some time and going down to minus E immediately. But this signal which is given here, it is not like that. It is slowly rising to plus E, then going to minus E with respect to a potential 0 volt. Let us say for this kind of circuitry with an analysis of this diode arrangement where only small incremental thing is made there, that this potential is kept here in place of straight shot to it like earlier circuit we considered. This much only. Remaining analysis and idea, everything is same. So, first I will see what is the difference. Okay. So, in this kind of circuit analysis, first you will see that if some potential V0 has come at the output, what is it basically? Earlier it was plus Vf, because diode was connected there which was in forward bias, so it went to plus Vf. If it is not forward biased, then diode is open. So, whatever be the input, output will be exactly same. Please try to get the idea. Here I am not going to the complex things inside. I am trying to bypass those complex things because it is not required at all. But to grow the confidence, we need some analysis there. Okay. So, in this circuit, what will be your approach? Maybe the signal has gone this way. You will try that if output voltage has come something for this diode forward biased, which will give Vf potential here across it, then what is the output? What is the other case? If the diode doesn't conduct, then it is open. So, no need to think about this complex part, remaining R and C only. Okay. So, let me first analyze if it is Vf, it is forward biased, and the potential V0 I need to find out. How much it is? Vf plus Vb1, that will be the V0. When it is, when the diode is forward biased or the Vi is a positive potential which is quite above Vf is applied, say. Input potential, if it is applied beyond this, then this will conduct and the potential will become Vf plus V1, which will be the output, which is the limit at which the clamping will happen. What is about the potential which is below that? So, if I want to draw the output, I am saying maximum value is Vf plus Vb1 at peak, means here. Now, if it is less than this, if this potential is less than this potential, then what will be this output here? It will be following the input with this 0 volt. What is the maximum value here? Oh, sorry, not this 0, this is 0. it will go up to this potential. Now remaining part for which this diode is open, if the diode is open, it will follow the exact path. So the output what you will get there, that's supposed to be the input, just like input where the potential difference between these two again should be 2E. But the limit of going this up to plus Vf plus V1 and this part from here to here, how much it will become? 2E minus Vf plus Vb1. I am not going to the internal discussions there. Just like earlier idea what we had, that it will, since it is a clamper circuit, maybe because of some bias here Bv1 it is there. If it would be 0, then what would be the clipping, what would be the clamping at Vf, the circuit what we have already discussed. Now that I have kept above of Vb1 also. So Vf plus Vb1. With that idea only I am analyzing the circuit. I am not going to discuss each and everything of it like earlier. Since I have some results, I am using those results that now the clipping will happen at Vf plus Vb1, not Vf like earlier. Now if it has gone like this, where the total swing should be conformed to E, so it must go less than this one, 2E minus of this, but the polarity is opposite. Same idea I am putting here in terms of only this bias part. I never analyzed anything there. Okay. Again, another bias part with Zener diode. Now, if you remember the discussion for clamping circuit, a clipping circuit with Zener diode, we were connecting one Zener diode in this direction where P up and down, and another one was opposite to it. But it was working basically one diode in forward bias, one diode in reverse bias, because Zener is basically used for reverse operation. Say in this we have put this kind of ordinary diode only to work. So what should be the polarity for the other one? This is the Zener with Vz, which is connected to this circuit. What is the purpose of Zener? Because in place of external source of Vb1 which we have considered earlier, now we have put one Vz there. This much only is the difference, nothing else. Okay. So analysis will be again like earlier, when the output will be fixed like Vf and Vz. First that I have to find. If it is not satisfying, that remaining are either this diode or this diode is not in conduction, so it is open, so this circuit is just open, no need to consider about it. Okay. So only thing is that I have to consider that if this is conducting and this is also conducting, for that what potential should I apply across it? One is plus Vf, another is plus Vz, so that this become reverse bias with breakdown Vz. So what should be the output value? Vz. For that, what should be the potential at the input? That should be a positive potential. If it is positive, then only this positive voltage has gone there. If it goes beyond Vf plus Vz, then this conducts and output voltage become V0. This is the maximum value. Okay. Now, if I consider this thing with this input, where should I draw the line? Like earlier, it will be going Vf plus, I had V1, I will be putting Vz, and remaining thing I will be discussing like earlier. The peak will be minus 2E minus Vf plus Vz. Okay. If anybody has any confusion in between, I will suggest Please try by yourself to analyze each and every point of this function. You should get. If it is not, we will again discuss. Okay? Thank you for today.